Take a nut and file away the threads on opposing sides. Then take a corresponding threaded rod and grind it flat on opposing sides as well. When the threads of the nut are offset by 90 degrees to the threads of the rod, there is no thread engagement, allowing the rod to slide in and out very quickly. If I now give the rod a quarter turn, however, the threads engage, preventing the rod from moving with respect to the nut. If we drill a hole through the bottom end of our vise and then embed the nut on the inside face of the front jaw, we now have a variable spacer that can be quickly adjusted to account for different thicknesses of material we might be clamping on the upper portion of the jaws. This is an alternative solution to the sliding rods, opposing wedges, cross mechanisms, and pin boards that are usually employed to keep the jaws parallel. So that's the general idea. Now if you'd like to implement this solution yourself, there are a couple of pitfalls that I'd like to warn you about, starting with the binding problem. Now this binding problem occurs because we're trying to engage 4 threads simultaneously. Now if the threads on the rod are aligned with that of the nut, then we don't have a problem and the rod will rotate. But if they're misaligned, then when you go to rotate the rod, you're going to get this binding issue. Now the threaded rod can only be advanced and retracted in increments of the thread pitch. And so if the distance between our 2 jaws is not set to a multiple of that thread pitch, then when we advance the rod forward and try to turn it, the threads on the nut and rod aren't going to be aligned. Now this also means that if the width of our workpiece isn't a multiple of the thread pitch, then the amount that this rod is projecting from the inside face of the front jaw won't exactly match. But realistically, this isn't so much of a problem for clamping because the difference between the two is negligible. Now, to prevent the rod from binding, we could just finesse it backwards slightly until it rotates, and that's a fairly easy solution. But because I can't resist a puzzle, I was curious to know if there's any way that we can alter the geometry of our rod and its corresponding nut, that sounded wrong, in order to mitigate this binding issue. Also sounded wrong. So while we can't change the likelihood that the threads end up aligned, what we can try to do is change the frequency with which the threaded rod slips. So if I offset the threads only slightly and I give the threaded rod enough torque, you can see that it slips into alignment like that. Now whether or not it slips is a function of how these flat triangular facets on the rod interface with the blue facets on the nut here. And so the question that I had is it possible to file these triangular facets into a sort of taper so that they deflect into the threads on the nut with greater facility? So this is the thread geometry that I've intended to go with. You can see it at the front half of this rod while the back half has been left unchanged. And the intent with this is to make the rod slip backwards, because we can't have the rod slipping forwards. If the rod tries to correct the alignment by slipping forwards, it's going to run into the fixed jaw of our vise, and so the geometry needs to be such that it causes it to go backwards. So now we just need to come up with a way of measuring how much more slippage occurs with the front half than the back half. And this entire assembly is simply here to allow me to move the rod back and forth in a more controlled manner, and I can do that because this wheel has a nut in the middle, and if I keep the nut pressed against this block, and I prevent the rod from rotating, I can control its lateral position by spinning this wheel back and forth. Okay, so starting with the threaded rod you just saw me install, we're going to start with the back half, so the section that's not altered in any way. And to begin, we're first going to find where the alignment is between the threads. So we're going to engage the threads, and then we're going to slowly rotate it clockwise, and as we do, the value on the dial indicator is going to increase so long as the threads are engaged. So when the value on the dial indicator stops increasing, we know that we're disengaged and that we're right at the point where the threads are aligned. So that would be my 0 right there. So now I'm going to advance this to 10, so 10 thou offset, and you can hear the difference. There's a little click as the threads slip against one another, but it rotates fine. So now let's go to 20. Okay, and 20, I'm twisting this quite hard and it no longer is slipping. Okay, so now we're testing the front half of the rod, the one that was modified, and we're first going to find our 0 the same as before. We're at 0, and just to confirm, there's no resistance when I rotate this because the threads are aligned. So now let's go to 10. And you can hear, besides the squeak, very little resistance. Now let's go to 20. And 20, it's rotating just fine. So let's go to 30. There's a little bit more resistance, but it's still going just fine. Let's go to 40. Okay, 40, we're getting a big click, but it is still slipping backwards. So 40 again. So now let's go to 45. 45 is slipping. Slips. Now let's try 50. Okay, now 50 is actually the limit that we can get this to go, and the reason for that is the thread pitch is 50, so that's the maximum misalignment we can correct for. I also wondered if we could simply alter the cross-sectional geometry of our components in order to mitigate this binding problem. And so I tested all three of these cross-sectional geometries, and the one that takes the least effort to make is this one, because we're not really grinding into the center of the rod, we're just grinding deep enough to get rid of the threads. And they all performed about the same, getting stuck at about 20 thou offset on the unaltered section of the rod. So I'd recommend that you go with this one. As it concerns the nut, however, there is a geometry to avoid, and it's the one on the left you see here. So with this style of geometry on the nut in combination with this specific rod, as the rod rotates, the points of the rod here dig into the slope, and this is just not conducive to slipping like the other geometries are. So this will bind quite easily, and on the jig that I showed you, this one only managed to make it to 10 thou offset. So these are the geometries for the components that I would suggest that you go with, and if you'd like a more concise form of all this information, there's a PDF in the description below. Now, the other obvious pitfall is how much force can these threads sustain before they end up stripping. The smaller the diameter of the threaded rod we use, the less work we have to do to get it to assume the required geometry, and the finer the adjustment becomes. So how thin of a rod can we get away with using? So I learned a little bit about material strengths in trying to answer this question. For low to medium carbon steel, that would be the material that a grade 2 bolt or nut is made out of. The tensile strength is 60,000 to 74,000 psi. Now the shear strength for steel is 60% of the tensile strength, and so if we were to take 60% of this lower value, we would get a shear strength of 36,000 psi. So what does it mean to say that the shear strength is 36,000 pounds per square inch? Well, in this depiction I have two plates and they're held together by a pin. If I were to pull on this plate hard enough to get this pin to shear, it would shear along this shear line, which in 3 dimensions would be a shear plane. Now I've made the diameter of this pin such that the area of this shear plane is 1 inch squared. So all this number means is that I would need to pull with 36,000 pounds of force on this plate in order to get this pin with a cross-sectional area of 1 inch squared to shear. So now that we know what it means to say that the shear strength of our rod is 36,000 psi, we now need to calculate the area that's being sheared. So suppose that I were to pull on this rod downwards until it were to shear completely. What I would be left with is just a cylinder. That is, if we accept that the shear line is at the base of these threads. And on that cylinder would be the remains of a spiral. In 3 dimensions would look something like this. Now note that in this example I have a considerable amount of space between my spiral, while here the spiral would have no space between it whatsoever. But this will suffice for the sake of explanation. So the shear area that we're trying to calculate is simply the area of this red helical band you see wrapped around this cylinder. So what is this area? The area of that red helical band is simply the area of a parallelogram, where the base of the parallelogram is equivalent to the hypotenuse of this triangle. Now we don't actually need to calculate this red shear area for ourselves, because if we go on the internet we can find that information on a table such as this one. So on the left you see different diameters of bolts. These are all UMC style threads with their corresponding threads per inch, and in the center column here you have the shear area per inch of engagement for these different sized bolts. Now it should be noted that the values on this table assume a length of engagement of 1 inch. And to understand what that means, we need to know what length of engagement is. Length of engagement is the distance along the axis of the bolt or threaded rod for which we have thread engagement. So the length of engagement in this example would simply be the width of this nut. So to answer our original question, how thin of a rod can we get away with using, I made this table, the link to which is in the description, and for a 3/8 inch rod at 16 TPI, the shear area is 0.576. Now the shear area times 40% to account for the fact that 60% of the threads have been removed gives us a shear area of 0.230. And if we multiply that by 36,000 psi, we get 8,294. Now, this would be if the nut were 1 inch wide, because this number is valid for 1 inch of length engagement. In actuality, the nut is only 21/64 of an inch wide, and so if we multiply this value by 21/64, we get 2,721, which is to say that unless your vise outputs more than this amount of force, a 3/8 inch rod, which is not what I used in this video, I used a 1/2 inch, is sufficient, and the threads will not shear. Now, I also did the math for different sizes in case you have a different application in mind, and I also did this for metric. Now, the question that I have is, how do I know that I'm not full of shit with these values? And ultimately, the answer to that is because if I am, one of the engineers among you is going to leave a scathing comment down below telling me what I got wrong. And when I say scathing, I really do mean scathing. Because if you're telling me something that I did wrong, you're ultimately still doing me a favor, so use as many pejoratives as you'd like. Don't worry about offending me. My dad's an engineer. Okay, so the way I confirmed the shear area values on that table that I showed you earlier was first by finding the equation for shear area on the internet and then inputting the values that you see here for this equation and seeing if I got the same result, which I did. But this by itself still doesn't tell me if my geometry presentation was correct. And so let me show you how I went about verifying that, even though it's kind of way beyond the scope of this video at this point. So does this equation, which I must admit does not look like the area of a parallelogram, really equal the area of this parallelogram? Well, to answer that, we first need to understand the dimensions of our triangle. And so the y dimension is the length of engagement, as I mentioned before, or the height of our eventual cylinder. Now, the length of this base here is a little bit more difficult to calculate. Let's start with d1 max, which is the maximum minor diameter of the nut. Now, you may be wondering, why are we taking into account the dimensions of the nut if we're talking about the shearing of the rod? Well, where the rod shears depends on where the nut is pressing on the rod, and that depends on the geometry of the nut, of course. And so d1 max is the maximum minor diameter of this nut. Maximum alludes to the fact that all of these things have tolerances that they're built to, and so the maximum tolerance allowed for the minor diameter is this dimension here. And the reason that diameter is important is because if we now overlay the rod, you'll notice that the maximum minor diameter dictates where the shear line is going to be along these threads. Now previously I depicted the shear line as being right over here where this black line is, and that would in fact give us a cylinder, but in actuality if we were to shear this right now, the shape we would end up with would look more like this. But you can imagine that these gaps were filled in because we don't actually care about the area that pertains to those gaps, and so you could consider these yellow stripes going across here to be analogous to the yellow stripes that I have on my cylinder. So now that we've established that the diameter of the cylinder is d1 max, the circumference is going to be d1 max times pi. Now this very long triangle doesn't wrap around the cylinder just once, it wraps around multiple times. And so to figure out the dimension of this entire triangle, what we need to do is take the circumference and multiply it by the number of times that the parallelogram makes it around the cylinder. Now p is the thread pitch, which would be the distance from crest to crest. And for every time that the parallelogram wraps around the cylinder once, that equates to 1 thread pitch worth of vertical travel. And so if we take the total amount of vertical travel, or the length of engagement, and divide it by the thread pitch, we get the number of times that this parallelogram wraps around the cylinder, which times the circumference gives us the dimension of this part of the triangle, because for every time that it wraps around, that equates to 1 circumference worth of x travel. So with this, we can account for the hypotenuse of this triangle by using Pythagorean theorem to calculate it, but we still haven't accounted for the height of the parallelogram, and the area is base times height, so we need to. Now the height, which I've depicted with this blue line, is not something that we can readily ascertain by looking at this model, but we can ascertain what this green line is. I'll let you have a guess as to what this green line is, but if you just want to know, this green line, which would pertain to this line here, is the shear line that goes across one of the threads. And so what we need to do is calculate how long this shear line is, then use some trigonometry to calculate how long this height is, and then multiply that by whatever the hypotenuse ended up being to get the area of our parallelogram. So how do we calculate the length of this shear section that I've depicted in green? Well, to accomplish this, we're going to factor in the single variable that we haven't yet accounted for in this original equation, d2 min. Now, d2 min is the minimum pitch diameter of the external thread being the rod's threads. Minimum, again, pertains to the tolerances to which these are built. But what is a pitch diameter? Well, the pitch diameter is kind of like the intermediary between the major diameter and the minor diameter. The minor diameter is the shortest distance between two opposing points on the rod, and the major diameter the largest distance between two opposing points. So, this brown line here representing the pitch diameter, I've depicted here as this brown line here. Now, it's called the pitch diameter because it's related to the thread pitch, the distance from crest to crest, in that this solid portion of this line is the same length as the thread pitch. And you know that because this point is offset from this one by the same amount that these 2 points are offset from one another. Now, the length of this line is bisected by this flank, by the flank of this thread, and that's what makes it the pitch diameter. And so we can calculate the shear section simply by figuring out the difference in length between the shear section and p over 2, which we already know. Now, why is that easier? Well, it's easier because if we look over here, the difference in length is the sum of the short sides of these two triangles. Now, if we zoom in on this triangle, the long side is equivalent to d2 min, which is this line up here, minus d1 max divided by 2. Divided by 2 because this is the difference in the radius, and these are diameters. Now, since we know that this is 30 degrees, we can do tangent of 30 degrees to figure out the ratio between the short side and the long side. Because we know the long side, we can calculate that quite easily. And then if we take this distance and multiply it by 2 to account for the two triangles on either side, we get the length of this shear section. Now, multiplying by 2 and dividing by 2 are opposing operations, so in the actual equation, what you just end up having is 0.57735, which is equivalent to tangent of 30, multiplied by d2 min minus d1 max. 1 over 2n is simply another way of writing p over 2. Because n is the threads per inch, 1 inch divided by 13 threads, let's say, is this value here, which is equal to p. So 1 over n is equal to p. 1 over 2n is equal to p over 2. So everything in these parentheses here is just p over 2 plus the length of these two short sides of the triangle. Now at this point, what I should have done is said, well, shit, I've already accounted for everything between these parentheses, so why don't I just stare at the remaining part of the equation for a bit and try to figure it out that way? But what I did instead is I insisted on going about this the way I had originally planned, which requires that I now calculate what the height of the parallelogram is, given what the length of this green shear section that we just calculated is. So the takeaway from this unnecessary digression into a geometry problem that was tangential to the original point of the video is that there's an easy way to do geometry problems and there's a hard way. I figured that the easiest way of solving this was by looking at the two-dimensional model, but I was wrong. The easiest way is by looking at the three-dimensional model. The area of this cylinder is the area of this spiral plus the area of this spiral. So rather than calculating the area of either one of these spirals, if I were to simply tell you that the area of this yellow region is twice that of the red region, then to calculate the area of either one, you would just need to multiply the entire outer diameter area by the ratio between these two areas. We could have done that if we had simply realized, or more correctly, if I had simply realized, that this green line here is the exact same line as this green line here. Now, this point to this point is the thread pitch, and this is the shear section. So the ratio between the area of the yellow region and the area of the red region can be rephrased as the ratio between the length of this line and the length of this line. And if we look at this model, it's clear that the length of these two lines added together is the thread pitch. So if I had simply taken the shear section and divided it by the thread pitch, I would have gotten the proportion of the cylinder that's occupied by the spiral that pertains to this shear section. And if I had just multiplied that by the original area of the cylinder, I could have arrived at this much more quickly. So what I've done here is I've taken this original equation and I've rephrased it in terms of P, and then I've taken 1 over P, which is equivalent to N, and I've placed the P down here. Now, if we look at this format of the equation, it becomes very clear that what we have is essentially the shear section, which is everything in the numerator here, the length of this line, divided by P, which is the length of this dashed line plus the length of the shear section line. And that gives us the ratio between the areas on the outer diameter of the cylinder. So now we just multiply that by the outer diameter area of the cylinder, which is of course just the height, LE, multiplied by the circumference, pi times d1 max. In short, just use the 3/8 inch rubber. That was exhausting and my brain hurts, so I'll keep the rest of this brief because this video is getting way too long. The hole in the nut is not necessarily concentric to the periphery of the nut, and so if the hexagonal cavity that you chisel into your vise is concentric to the hole that you drilled, that doesn't necessarily mean that the threads on the nut are going to be concentric to the hole that you drilled, which means you're going to have a misalignment between the rod and the nut. So the way to get around that is to take the nut that you intend to use for this application, screw it onto the rod, and then while holding it in the orientation that it's going to be installed, overlay that where you're going to chisel your hexagonal cavity, and then trace around the nut so that you know exactly where it needs to be positioned. Okay, thank you guys for watching, and I'll see you guys in the next one.